Hi everyone. So this will be my review of representing functions. And before we get to representing functions, and this will typically be using graphs, let's first review what type of functions we're going to be dealing with. The first kind are the polynomials. Oops. That's an I. Let me try that again. Polynomials. Right. I think I can spell this. Right. So you've seen these before. So a typical polynomial might be, 8x to the fourth minus 7x cubed plus 13x squared plus 5, right? So anything of that form, basically a bunch of terms where you have some coefficient, say an, times x to some power, and then you just keep adding them up, right? And usually the exponents go in decreasing order like this. That's sort of the standard way to write it, until you just get to the constant term, say a0. Right? So this is, I'll call it P for polynomial, right? This is a typical polynomial. Another type of function we've already encountered are the rational functions. Right? And these are just polynomials divided by another polynomial. That's supposed to be a P. Let's try that again. And I'll use Q for the denominator. But P and Q are both polynomials, right? So a typical example might be, x squared minus 4x plus 4, all divided by x cubed plus 8. Right? So this is a typical rational function. Right? And then you have the more general algebraic functions. Right? So these could involve things like square roots or cube roots. Right? So I might have, x times the cube root, x times the cube root of 4x plus 1. Yeah, so be careful you don't write this sloppy, because it could look like x cubed times the square root of 4x plus 1 if you put the 3 in the wrong place. Right? So these are both algebraic functions, but be careful where you put the 3. Right. And even though we won't be seeing these for a while, till the very end of the class, you have your exponential functions and your logarithm functions. And these are just inverses of each other. So we'll review all that, toward the end of class. Exponential functions could look like this. You can have, say, f of x equals 2 to the power x, right? Or, even 3 times e to the power x minus 4. Right? So these are all exponential functions as long as the variable is in the exponent. Right? And then you have your logarithm functions. So that might be log base 2 of x, or it could be log base e of x. Running out of letters here. So j of x might be log base e of x, which is also better written as ln of x. Right? So natural log just means log base e. Okay, so we'll get to those a little bit later. Right, so the next kind, and these should be familiar, these are the trigonometric functions. Right? And I'll review these in the next video, but for now, you should remember, right, sine of x, cosine of x, and then tangent of x, which is just sine over cosine. Cotangent of x is cosine over sine, or just 1 over tangent. Right. Secant of x is 1 over cosine of x, and cosecant of x is 1 over sine of x. Okay, so these are going to come up again and again. Okay, let's start with a simple example. Find the linear function whose graph contains the points -1, -11, and 3, 5. Okay, so first thing is, what do we mean by a linear function? We mean that the graph is just a straight line. And for that, you should recognize that this is just mx plus b. Right? In the old days, they might just say find the equation of the line. Right? So that would be y equals mx plus b, same thing. So we just have to find m and b. And you should remember m is called the slope of the line. Right? You remember that as rise over run. And the rise, of course, is the difference in the two y values, so delta y. And the run is the difference of the two x values, so delta x. And you probably remember that as y2 minus y1 over x2 minus x1. So again, which one is which is up to you. For the first point, I'll call this x1, y1. And then the second point will be x2, y2. So just to make it clear, we have our values, right? x1 is -1, y1 is -11, x2 is 3, and y2 is 5. So you plug all those numbers into the formula for slope, and what do we get? We get 5 minus -11 divided by 3 minus -1. So that's 16 over 4, which is just 4. Right? So we know m is 4. So that's half the puzzle right there. The function is going to be, instead of mx plus b, it's 4x plus b. So now we just have to find b. Remember, b represents the y-intercept. So 0b is called the y-intercept. It's where the line crosses the y-axis. Right? And there's a number of ways to do this. I think the easiest way is just pick either of the 2 points. So I'll pick the second point. And we know that if x is 3, y is 5. So if I replace x with 3, I get 4 times 3 plus b. But that has to equal 5. So we can just solve for b. Right? 12 plus b equals 5. Subtract the 12 from both sides. And we get b is 5 minus 12, so -7. Right? And so that has to be b. So now we know m is 4 and b is -7. So the linear function is 4x minus 7. Okay. So again, I know you've done this before. Hopefully this is easy. But this is also a good review of slope. We're going to see this concept of slope come up again and again. So don't forget, slope is rise over run, change in y over change in x, or the difference in the y's divided by the difference in the x's. Okay, so the next thing we want to do is graph the piecewise defined function, f of x is 2x minus 1 if x is greater than or equal to 2, and it's equal to -1/2 x plus 4 if x is less than or equal to 2. Right. So in the last question, right, I just asked for the equation of the line as a function, but we didn't actually graph the line. So here we're going to graph actually 2 lines, but it's 2 different pieces of the same graph. So I'm going to try to do this carefully here. So pretend this is my y-axis. This is my x-axis. I hope this is good enough. So 1, 2, 3, 4, 5. This is my scale. Let's go -1, -2 here. And then the vertical scale. So we have 1, 2, 3, 4, 5, 6, 7. Okay. All right. So, yep. Let's start with the line y equals 2x minus 1. So we know the slope is 2 and the y-intercept is 0, -1. So here's 0, -1, and then go up 2, right 1, up 2, right 1. Right. So the rise is 2, the run is 1, right? 2 over 1. And that's going to give you all these points here. So, and so the line looks something like this. Okay. Unfortunately, I hope you didn't use a pen when you're doing this, because we're going to have to erase. Notice this condition says that this is only valid if x is greater than or equal to 2, right? So here's x equals 2. Everything less than 2 is not really there. So we have to erase everything that's less than or equal to 2. I don't know how I'm going to do this, but I'm going to take my eraser here and erase all this. All right, sorry about that. There's going to be residue left over, but that's inevitable here. All right. So yeah, what we should have done, of course, is just started the line at x equals 2 here, and then just graphed where x is greater than or equal to 2. Right, so that includes this point here, which is the point 2, 3. All right. Now the other piece is the line y equals -1/2 x plus 4, but this is only valid, right, if x is less than 2. So in other words, everywhere else, right? So in this case, the y-intercept is 0, 4, and when x is 0, 0 is less than 2, so we can plot that point there. And now the slope, right, is -1 over 2. So we can think of this as going down 1, right, and right 2. But if we go to the right, that's going to be where x is greater than 2. So maybe we should have thought of this as going up 1 and left 2. So up 1, left 2, up 1, left 2, and so on, right? A bit of mess here. Okay. Yep. So connect the dots, and you get this line here. Right? And notice that if I could plug in 2 into this piece of it, right, I would still get, oh. No, I wouldn't get 3, would I? Oop. So that was, I did not expect that. Yeah, 4 minus 1 is 3. Okay, I had it right. I was second guessing myself. Yeah, so if I could plug in 2, well, if you plug in 2, right, it's 2 times 2 minus 1. 4 minus 1 is 3. But if I did plug in 2 here, even though you're not supposed to, right, you get -1 plus 4, which is also 3. All right. Okay, so the two pieces meet up at the point 2, 3. Right, but that didn't have to happen. In fact, let's look at another example, and we'll see that that's usually not the case. Okay, so now we have a function that's 3 separate pieces. It's x squared if x is less than 0. It's 3 if x equals 0. And it's x plus 1 if x is greater than 0. Okay, so try to be a little less sloppy here. Oh, it's so hard to draw a vertical line on this. All right. All right, so that's my x-axis, that's my y-axis, and then we'll use the usual scale here. So each of these is just 1 unit. Okay. So y equals x squared. Right, we know what that is. It's a parabola, right? And the vertex is at 0, 0. But notice this is only valid when x is less than 0. So that's just the left half of the parabola. So it looks something like that. Right? And keep in mind, at 0, you can't plug in 0 here, so there's a little hole in the graph, which I will try to make it clear that there's nothing there. Okay. All right, so now what happens when x equals 0? Well, y equals 3. So 0, 3 is a point on the graph. 0 and then up 1, 2, 3. So that's just one single point. All right. And then finally, when x is positive, y is equal to x plus 1. Okay, so that's just another straight line with slope 1, and y-intercept is 0, 1. If it had a y-intercept, which it doesn't, right? You're not allowed to plug in 0 here. But you can plug in any positive number, right? So you can plug in 1. You get 1 plus 1 is 2. You plug in 2. 2 plus 1 is 3, 4, 5, and so on. So it's just going to be this straight line here. But you never make it to 1. So we leave a little hole there at 1, at y equals 1, right? So there you go, right? So that's the graph of this piecewise function. And again, it's a good example of something we'll see when, later on when we talk about limits. But yes, so in this case, it's kind of a mess, right? At x equals 0, y is equal to 3. But if you look a little bit to the left, it's going to be pretty close to 0. If you look a little bit to the right, it's going to be pretty close to 1. But you never make it there, right? Right. After all, remember that a function can have only one y value for each x value. So if I ask the question, what is g of 0, right? Right? Well, 0 is not less than 0. It's not greater than 0. It's equal to 0. So there's only one answer here. It's got to be 3. Okay. Yep. So it might look like it gets close to 0 or 1, but it isn't, right? Those are, you can't fill those points in. Because if you fill the points in here, it's no longer a function. Right? Because now you're saying g of 0 is also equal to 0, and g of 0 is also equal to 1. That can't happen for a function, right? You can't have 3 different y values, or even just 2 different y values for the same x value. Right? So it has to be defined unambiguously. Okay? Which means, just erase the 2 points here. And now it's correct. Right. Yeah, remember, a function also has to satisfy, the graph has to satisfy the vertical line test. Every vertical line can cross the graph once and only once. So again, let me make the same mistake here. If I did fill in these 2 points, it would now fail the vertical line test, because the y-axis is a vertical line that crosses not once, not twice, but 3 times. Right? You can't cross, right, the graph more than once. And so once again, these 2 happen to be, or these 2 here have to be holes. Right? Holes in the graph. Oop. Okay, so right, that can happen when you have piecewise functions, or even other types of functions that will have holes in it, as we'll see later. Okay, one more example, and this should be an easy one. It's one that you probably have seen before. Absolute value of x, right? So this is the absolute value function. And its definition is just the piecewise function. It's x if x is greater than or equal to 0, and negative x if x is less than 0. So when x is positive, it's just y equals x. Right? And when x is negative, it's y equals negative x, which has a slope of -1. Right? So it's just this v-shaped graph. Right? Right. So remember, when you take the absolute value of a positive number, you just get that number back. If you take the absolute value of a negative number, well, remember, -3 is less than 0. So if x is -3, we have to take negative -3, the opposite of -3, which becomes +3, right? So yeah, absolute value simply changes a negative to a positive. And if it's positive, it just stays positive, right? So yeah, so the 0.55 should be on the graph over here. And if x is -3, y should be +3. So -3 is another point on the graph. And of course, the absolute value of 0 is just 0. So the origin 0, 0 is a point on the graph as well. Okay. Okay, so another topic in this section is transformations of graphs. And, you know, it can be useful if you want to quickly graph certain functions, but I don't think I want to spend a whole lot of time on it other than just a very quick review. So given a function, let's say I have this function f of x here in green, and I want to graph, let's say y equals f of x plus 3. Okay, so all we're doing is taking the graph and adding 3 to all the y coordinates, right? And that has the effect of just shifting this graph up 1, 2, 3 spaces. So it's the same graph, just moved up 3 spaces, let's say, right? So likewise, if you have f of x minus 3, well, you're subtracting 3 from all the y coordinates. So that just gets shifted down 3 spaces. Right? Okay. A little trickier, though, if I want to graph y equals f of x plus 3. So now x plus 3 is in the parentheses. Okay, so that you have to think about a little bit. Right? Because it looks like, well, if you know, it's going with the x, this is not going to be going up and down, it's be going, you know, left and right. But which way? Left or right? So if you thought it's to the right because, well, positive is to the right, negative is to the left, that's a good guess. Unfortunately, it's wrong. You're shifting it to the left 1, 2, 3 spaces. Okay. So it just gets bumped to the left 3 spaces. Right. So why is that, right? If it's x plus 3, right, I would have thought that would shift to the right, right? 3 spaces to the right. So think about this in terms of the domain, right? And again, I didn't write a scale here, but think of the original graph, the green graph here, right? This point here is the endpoint of the domain, right? Let's say it's at x equals -2, right? So if x is -2, right, and y is 0, on the original graph we have the point -2, 0. Right? What would that be on the transformed graph? Right? So you might think, well, right, if I add 3, -2 plus 3 would be +1. It'd be shift to the right. But think about what you're plugging in now. You're plugging in 1. And if 1 is equal to x plus 3, right, you're going to get x equals -2, right, which is over here now. Did that make sense, right? So in other words, right, whatever number this is, right, what I just made up 1, I guess. right? If that's the new x, right, then that's what x plus 3 equals. All right, confused? So, all right, let's try it a different way, right? If I want this to equal 0, what does x have to be? Right, so x plus 3 has to be the same as the original x, which is negative 2. Right, so what is x going to be? Well, take away 3, x has to be negative 5. So you're shifting from negative 2 to negative 5. And that means you're shifting to the left. So this shifts to the left 3 units. Oops. Right. So what would happen if you want to shift to the right? Well, then you're going to have to subtract 3. So this shifts to the right. 3 spaces, 3 units. Okay, so again, how do I get 0? When x minus 3, right, is equal to its original value, negative 2. And when you add 3 to both sides, you get x equals 1. So that does shift to the right 3 spaces, from negative 2 to negative 1, 0, 1. Okay, and the graph would look something like this. Shifting to the right 3 spaces. Okay, and there's other ways to transform graphs other than shifting. You can do a reflection. Right, you can do a reflection through the y-axis. And that's just taking x to negative x. So make x negative x. If you want to do a reflection through the x-axis, then just take the whole thing and flip it. So put a minus sign in front. Right? And you can also do stretching and shrinking. And again, there's 2 varieties. You can vertically stretch. Right? By a factor of a. So that just multiplies the entire function times a. Right? Oh, and a would have to be bigger than 1 for it to be a stretch. It would have to be less than 1 if you're shrinking or compressing. Right? And then if you're doing this horizontally, it of course is the complete opposite. So if you want to do a horizontal stretch, right, by a factor of, let's say, b, where b is going to be bigger than 1, then you multiply x by 1 over b. Right? And if you want to do a horizontal shrink or compress, again by a factor of b, so b would be less than 1. Right? Well, same thing, right? You multiply by 1 over b. Right. Right. So you can play around with this in the homework. I really wouldn't worry too much about that if you're confused about which way it's stretching and shrinking and all that. I mean, I'll do one quick example, and hopefully that'll make a little more sense then. Okay, so let's just graph these 3 functions here, right? Y equals square root of x. So I hope you know what that looks like, right? Square root of 0 is 0, square root of 1 is 1. The square root of 4 is 2, and the square root of 9 is 3. So it has this basic shape here. Okay. Now, what about the square root of 2x? Okay. Well, easiest way is just make a table, right? And if x is 0, y is still 0. But now notice what happens when x is 1. Y is going to be the square root of 2, which is a little bit bigger, right? And if x is 2, y is going to be the square root of 4, which is 2. So the graph will look a little bit like this. Oops, I think I'm going to have to erase the square root of x. Okay, so again, this will be the graph of y equals the square root of 2x. And just for reference, oops. Yep, this is the graph of y equals the square root of x, the original graph. Right? So notice what happened when we multiplied by 2, right? That's going to be a horizontal shrink by a factor of 1/2. And you can see that's what happens, right? The x values get cut in half, from 4 to 2, right? From 2 to 1, and so on. So this is horizontally shrunk by a factor of 1/2. Right. So for the green graph, it's going to be the opposite. If you multiply x by 1/2, it's going to be a horizontal stretch again by a factor of, well, by a factor of 2, right? 1 over 1/2. Right. So now, right, again, we still have 0, 0. But if x is going to be equal to 8, right, then y is going to be the square root of 1/2 of 8. Square root of 4 is 2. So we have the point 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, and then up 2. So that's going to be way over here. And so you can see that this is going to be horizontally stretched, right, by a factor of 2. All right, so hopefully that sort of untangles this mess about horizontal shrinking and stretching. So you have to be careful because you got to take the reciprocal. The vertical stretching and shrinking, I think, is pretty standard. You can do that with the same graph as well.